Some words in mathematics are dangerous. In this video, the dangerous word is conserved. Because conserved sounds like bookkeeping. Something is stored. Something is protected. Something is never lost. Energy is conserved. Momentum is conserved. Angular momentum is conserved. In school, these can feel like separate rules. Useful, powerful, but almost mysterious. Why should energy stay constant? Why should momentum be preserved? Why should a spinning object keep its angular momentum unless something interferes? For a long time, conservation laws looked like facts about nature. Then Emmy Noether revealed that they were also facts about symmetry. Not symmetry as a pretty pattern. Not a butterfly or a mirror image. But symmetry as invariance. A transformation that changes how we describe a system while leaving its laws unchanged. That was the deep idea. A conservation law is not merely a rule that nature happens to obey. It can be the shadow of a symmetry. Start with a simple experiment. Imagine a ball moving on a perfectly smooth table. Now imagine doing the same experiment 1 hour later. If the laws of motion are the same, then the system has time translation symmetry. The laws do not care when the experiment begins. Noether's theorem says that this symmetry is connected to a conserved quantity, energy. Now imagine moving the whole experiment across the room. Same table, same ball, same push, just shifted to a different place. If the laws are the same here as they are there, the system has space translation symmetry. Noether's theorem connects that symmetry to conservation of momentum. Now rotate the entire setup. If the laws do not care which direction the experiment faces, the system has rotational symmetry. That symmetry is connected to conservation of angular momentum. This is the astonishing pattern. Time symmetry gives energy, space symmetry gives momentum, rotational symmetry gives angular momentum. The conserved quantities were not isolated miracles. They were linked to transformations. But to see why this was so powerful, we need to understand what kind of mathematics Noether was working with. In ordinary mechanics, one can describe motion through forces. Newton's laws say how forces change motion. But by the 19th century, another language had become central, the language of action. Instead of looking only at force at each instant, mathematicians and physicists could look at an entire possible history of a system. A path. A motion from one state to another. The action assigns a number to such a history. The actual motion is the one that makes the action stationary. This is called a variational principle. It sounds abstract, but it is a way of turning motion into structure. The system does not merely move. It follows a rule about possible histories. Noether's theorem lives in this world. It asks, what happens if we transform the system, but the action stays the same? What happens if shifting time, shifting space, or rotating the setup leaves the mathematical structure unchanged? Noether's answer was, then something must be conserved. This is why conserved is a dangerous word. A conserved quantity is not protected by a cosmic accountant. It is preserved because the mathematical rules have a symmetry. The law does not change, so a quantity cannot change. The idea did not come from nowhere. Noether arrived in Göttingen in a moment when mathematics and physics were under pressure. Einstein's general relativity had changed the meaning of space, time, and gravity. David Hilbert and Felix Klein were thinking deeply about invariance, geometry, and the foundations of physics. There was a problem. In general relativity, energy conservation did not look the way physicists expected. The familiar conservation laws from older mechanics seemed harder to formulate. Was energy really conserved? Or had the new theory broken one of physics' central principles? Noether was asked to help because she understood invariance and transformations at a level few others did. And in 1918, she published a paper called Invariant Variational Problems. The title sounds technical, but behind it was one of the most profound ideas in modern science. Noether proved two theorems. The first theorem is the one most people mean when they say Noether's theorem. Continuous symmetries of the action correspond to conservation laws. The second theorem dealt with more complicated infinite-dimensional symmetries, the kind that arise in theories like general relativity and later gauge theory. Together, they clarified why conservation laws appear and why some conservation questions become subtle in deeper theories. But the first theorem alone changed how physicists understood the laws of nature. Before Noether, conservation laws could be treated as separate principles. After Noether, they could be seen as consequences of symmetry. This changed the question. Instead of asking only, what quantity is conserved? One could ask, what symmetry explains it? Energy conservation is no longer just a fact about energy. It is a sign that the laws are invariant under shifts in time. Momentum conservation is no longer just a fact about moving bodies. It is a sign that the laws are invariant under shifts in space. Angular momentum conservation is no longer just a fact about spinning. It is a sign that the laws are invariant under rotations. The conserved quantity is the visible trace. The symmetry is the hidden structure. That is why this theorem became so central. It connects mathematics and physics at a deep level. Physics asks what does not change in nature. Mathematics asks what transformations preserve structure. Noether showed that these questions are not separate. They are reflections of the same idea. The word symmetry had already transformed mathematics. It had become algebra through groups and transformations. Noether carried that structural vision into the heart of physics. A symmetry was not just an aesthetic feature. It was a machine for producing conservation laws. But the theorem must be stated carefully. Not every symmetry of an object creates a conservation law. A perfectly symmetrical vase does not automatically conserve energy because it looks balanced. Noether's theorem is about symmetries of the action, symmetries of the mathematical laws governing a system. And not every symmetry is the same. The first theorem concerns continuous symmetries, transformations that can be varied smoothly. A time shift by 1 second, or by half a second, or by a tiny fraction. A rotation by 90 degrees, or 10 degrees, or a very small angle. These smooth families of transformations are what produce the conserved quantities in Noether's first theorem. That precision matters. Because without it, the theorem becomes a slogan. And Noether's theorem is much more than a slogan. It is a structural statement about how laws are built. This is why her work had such a long afterlife. In classical mechanics, it explains familiar conservation laws. In field theory, it connects spacetime symmetries with currents and conserved quantities. In quantum mechanics and quantum field theory, symmetries organize particles, interactions, and possible laws. In modern physics, one often begins not by guessing forces, but by asking, what symmetries should the theory have? That question is Noetherian in spirit. The laws are constrained by what must remain invariant. The possible world is shaped by symmetry. There is also a human story here. Emmy Noether worked in a mathematical culture that did not easily accept women. For years, she faced institutional barriers that had nothing to do with the quality of her mathematics. Hilbert famously defended her presence in Göttingen. But the point of the story is not only that Noether was excluded. It is that, despite those barriers, she changed the structure of modern mathematics and physics. Her theorem on symmetry and conservation is only one part of her legacy. She also reshaped abstract algebra, rings, ideals, modules, structural methods. She helped mathematics move away from calculation alone and toward systems defined by relations. That is why Noether belongs naturally in Behind the Theorem. Her work does not simply add another theorem to a list. It changes how we see the laws behind the theorem. A conservation law no longer looks like an isolated commandment. It becomes a consequence of invariance. A quantity remains fixed because the underlying structure does not notice a transformation. Time can shift. Space can shift. A system can rotate. If the action remains unchanged, something is preserved. That is the structure behind the theorem. The dangerous word was conserved, because conservation is not only about something staying the same, it is about why something stays the same. Noether's answer was symmetry. Not visual symmetry, not decorative symmetry, but symmetry of the laws themselves. A hidden invariance that forces a visible constancy. That is why energy is tied to time. Momentum is tied to space. Angular momentum is tied to rotation. And that is why the theorem from 1918 became one of the deepest bridges between mathematics and the physical world. For more stories behind the ideas that shaped mathematics, subscribe to Behind the Theorem.